Hi guys, here is section 2. Now you're going to actually be introduced to the concept of a logarithm. So we are going to be looking at logarithmic functions. So logarithmic functions. So our goals, what is a logarithm? Write an exponential, which you saw yesterday, in log form. Write logs in exponential form. So these are sort of going back and forth. This is super important that you get comfortable going back and forth like this, and then evaluate log expressions. So let's take a look at how this all works, how this pans out. So what is a log? A log is an inverse of your exponential function. We know what inverse is. An inverse takes any function that is always increasing or always decreasing. You can reflect it over the line y equals x, and you will get the inverse function. Remember, that's when we switch the x and the y, and you then go ahead and solve for y. We've looked at those. So here is your exponential growth equation. If I reflect that over the y equals x axis, you get your logarithmic. So what happens is, just as we switch the x and the y, the domain and the range switch. Here's the domain and the range for your exponential. This is what we looked at yesterday. If y equals a to the x. We had the domain is all real, the x's are both positive and negative, but the y's are always positive. Well, in your logarithmic function, that is going to get reversed. So now the domain is only positive x's. So what happens is you have basically an intercept here along the y-axis. This is now an asymptote, sorry, not an intercept. An asymptote is now the y-axis, not the x-axis. And the range, which is now your y value, is going to be all real numbers. So it starts low, it comes up, it's going to cross here, and we'll talk about what that value is. Usually that will be at the point 1, 0, just like this would be at 0, 1, depending. And so let's go ahead and talk about a little more the form of your log equation as an inverse. So here's your exponential function, y equals a to the x. We've dropped the coefficient for a while, and I'm sticking with a just so it matches what your book has. I really liked having a b for the base, but your book tends to use a now for the base, so I'm going to kind of switch over to that. So y equals a to the base, that's your exponential. A logarithm, the way you'll read this, y equals log base a of x. Now, if I were to translate this, and again, I'm trying to keep with the way your book has it. I don't like that they write it this way because it doesn't really show the relationship. Your former exponent, actually, if I were to translate this, this is your exponent. This is the same as a to the y equals x. The whole point of a logarithm is to solve for an unknown exponent. So the exponent is out here on the other side of the equal sign. So that's where the inverse relationship comes from. You would switch your x and your y and solve for y. So as we go along, we have y equals, so here's your base. That is going to stay the same. So notice, so down here I kind of kept it in the same. So here is your base. Your base is always down low. So either the exponential or the logarithm. There's your base. Here is your exponent in both of these. So notice the exponent is on the other side. And then your answer, if you want to call it that, is y. So y equals 2 to the x is the same thing as log base 2 of y equals the unknown exponent x. And what we want to do is get comfortable going back and forth, writing one as the other. So let's get some practice with that, and then you get to kind of know what the format is. So here is the format again. So remember that your base is 2, the exponent is x, and our answer is y. So if I take 2 to the 4th equals 16, because 2 multiplied 4 times is 16, and rewrite it as a log, I have log base 2 of 16 is what exponent? It's 4. So now we want to go through and write some of these other ones in terms of logarithms. So 3 squared equals 9. All right, well, we know 3 squared equals 9. Let's write that as as a logarithm. So my base is 3, so that goes in this little box down here, log base 3. Now the answer here, so 3, the exponent is 2. Since we're solving for an unknown exponent, that comes out here, and the 9 goes here. So it's kind of almost like a cross multiplying. The exponent goes on the other side. So log base 3 of 9 is 2. That's how you would say that. So now if we do 4 to the negative 2, what is 4 to the negative 2? The negative means reciprocal, so that's going to be 1 over 16. So log, what is my base? It's going to be 4. And my answer is 1 over 16. So 4 to the what is going to be 1 over 16. That will be a negative 2, solving for that unknown exponent. All right, so now you know the answers here. It's just a matter of putting it in a new form. So now let's go backwards. Log base 2 of 32 is 5. What does that mean? That means my base is 2 raised to the 5th power is 32. Now I come down here, log base 3 1/3 equals negative 1. So we have 3, that's my base, raised to the negative 1 is 1/3. Okay. All right, so let's go to our next and see how we can make use of this to evaluate your log expression. So notice you have a strategy here. We're going to let x equal the unknown log. So notice I have a bunch of logs down here. So we're going to immediately start by just let x equal that unknown log. So each one of these, it's going to equal x. That's going to be your first step. Equals x, equals x, equals x. All right. Then we want to write the equation in exponential form. So here's an example. If I take log base 3 of 81, we write it equal to x. That's your first step. Now you have something on the other side, so you can write it in exponential form. So your base is 3. The base is 3 raised to the exponent x equals 81. Okay, well, we're beginning with ones that you should be able to figure out. So 81 is a power of 3. So we rewrite 81 as 3 to the 4th. And then it's exactly what you did yesterday. You can cancel out your bases, and we know that x equals 4. Okay? Oops, take that away. All right, let's go ahead and do a couple of these. So we have log base 4, 256 equals x. So I'm going to rewrite that in exponential form. Your base is 4 raised to the x equals 256. And we want to then rewrite 256 as a power of 4. So 256 is 4 raised to the, so 4 squared is 16, cubed is 64, so 4 to the 4th. So once you have the same base, you can cancel those out, and again we have x equals 4. So then we move on to the next problem. Log base 5 equals x. So the first thing is always set your equation equal to x, so you have something on the other side. So we want to ask ourselves 5 raised to the x, so the base is 5, raised to the exponent x equals 5. So rewriting this is pretty straightforward. So I wanted to point this out. So when we cancel this out, we get that x is 1. Anytime you see the base and the answer are the same, we know the answer is going to be 1. So that's going to be one that we want to definitely keep track of. Anytime you have these two match up, the answer is 1. So if I gave you log base 12 of 12, the answer, you can simplify that to 1. That's going to be a powerful identity. Okay, so let's continue on with these. Now we have log base 27 of 3 is x. We write it as an exponential. So that's going to become 27, that's our base, raised to the x equals 3. Okay, so now you have some choices, which one you want to write as which. Maybe you want to write 27 in terms of a base of 3. So we could do that. We can write 27 as that is 3 cubed. So 3 to the 3x equals 3 to the 1. So then, just like you did yesterday, we can cancel the bases, and we know that 3x equals 1, so x will equal 1/3. So the answer here would be 1/3. Anytime your base is bigger than your answer, you know it's going to be a fraction because you have to get smaller. You're taking a cubed root, is what this is saying. The cubed root of 27, remember that's if your exponent is a fraction, equals 3. So now let's look at this next one. We're going to raise this. This is 4 to the x equals 1/64. So if we write them with the same power of x, we have 4 to the x equals 64. 1/64 will be 4 to the negative 3, right? Because 4 cubed is 64, but this is a fraction. So that means we can cancel out our base, and we know that x is going to equal a negative 3. Okay? So you're utilizing writing a log as an exponential in order to evaluate it. You want to get really comfortable going back and forth. And that is the end.